What if the world you know, the blue planet beneath your feet, the familiar seas and skies above, was only a brief chapter in a much stranger, older story? Tonight, as you rest and let curiosity guide you, we journey back not thousands or even millions of years, but billions, to an era when Earth wore a different face entirely, the Proterozoic Eon, a span of time stretching from 2.5 to just over 500 million years ago. Imagine standing on its shores. The oceans are not the sparkling blue of postcards, but murky, metallic, and alien. The air is thin, holding only the first hints of oxygen, not yet safe or plentiful for creatures like us. Life exists, but it is microscopic. Colonies of bacteria weaving mats across tidal flats, invisible to the naked eye, yet already reshaping the destiny of the planet. Mainstream science presents the Proterozoic as a bridge, a transition between the simpler microbial world of the Archean and the explosion of visible life in the Phanerozoic. Textbooks describe it as oxygen's slow rise, continents gathering and splitting, and the first multicellular organisms leaving faint, ghost-like traces in the rocks. That picture is true, yet incomplete, for within those billions of years, Earth endured cataclysms that froze its seas, eruptions that blotted out the sky, and evolutionary experiments that may have flourished only to vanish without a trace. Close your eyes and sense it. Supercontinents, drifting like rafts, mountains rising where none had been, and glaciers grinding down across what may have been a frozen equator. The world was at once fragile and resilient, a place caught between silence and awakening. As you listen tonight, ask yourself, what would it feel like to walk across that frozen land, or to dive into those green oceans? Could we even recognize life as life, or would it seem like another planet entirely? Welcome, traveler, to a long-forgotten eon. Together we will trace the shadows of its seas, the breath of its air, and the secrets buried in its stones. Let this be your map across deep time. Now, let us begin with the forging of Earth's first great continents. If the Proterozoic Eon was a stage play of transformation, then its opening act was the quiet establishment of stability. For billions of years before, Earth's crust had been restless, fragile, and easily broken. Continents rose only to be swallowed again by molten depths like fleeting islands on a stormy sea. But during the Proterozoic, something changed. The planet began to hold on to pieces of itself. The restless child grew steadier, and the first true roots of land appeared. These roots are what we call cratons. Imagine them as the deep anchors of the continents, slabs of ancient rock that have endured the churning violence of plate tectonics. Unlike younger crust, which bends, warps, and is consumed, cratons are stubborn survivors. They are old beyond imagination, 2, 3, even 4 billion years in age. Their stability made it possible for the Earth to build lasting continents, platforms for the drama of life yet to come. Picture them rising in silence from the seas. Waves crash against unyielding rock, green tides swirling around shores that would one day host forests, mountains, and civilizations. But here, in the Proterozoic, they are bare and raw. No trees, no soil, no animals, only stone meeting sky, yet those stones held secrets, becoming the scaffolding upon which Earth's story would be written. Today, geologists travel to places like the Canadian Shield, the ancient heart of North America, where rocks older than 2.5 billion years lie exposed. In northern Australia, the Pilbara and Yilgarn cratons tell similar tales. In Africa, the Kapfor craton holds relics from a world before oxygen filled the air. These shields are like time machines, windows into Earth's earliest memory, written not in words but in minerals, isotopes, and scars of ancient collisions. By studying them, scientists can trace the chemical fingerprints of early oceans, the shifts in Earth's magnetic field, and the tectonic struggles that shaped the planet's skeleton. Each craton is not just a block of stone, it is a living archive. The zircon crystals found within them, tiny grains smaller than sand, carry whispers from Earth's dawn, recording the slow cooling of a once molten world. But beyond the data, there is wonder. To stand on such a shield is to stand where the earth itself first learned endurance. You can almost imagine the silence of that age, when continents were newborn and seas rolled under a sky without birds. Cretons remind us that while life may be fragile, the ground beneath it has its own kind of persistence. Speculatively, one might ask, if cretons are the roots of stability, could their presence have influenced where life flourished? Perhaps the shallow seas that pooled around their margins provided havens for microbial mats, feeding on minerals and sunlight. Perhaps without them, the Earth's surface would have remained too unstable, too chaotic for complexity to find footing. In the grand theater of deep time, the Cretaceans are not glamorous. They do not erupt or explode. They endure, yet their endurance gave Earth something priceless, permanent. Without them, there would be no continents to gather into supercontinents, no mountain ranges to rise, no ecosystems to cling to their surfaces. They are, in a sense, the bones of the planet, ancient, unyielding, and still with us today. As you let your mind drift across this vision of primeval Earth, consider the paradox. The most silent, steadfast stones were the ones that allowed the future to be noisy with forests, rivers, and human voices. The Cretans are the quiet guardians of time, anchoring a world in flux, and with their birth, the Proterozoic's long story of transformation could truly begin. The Earth is never still. Even when it feels immovable beneath your feet, the ground is quietly drifting on currents of molten rock deep below. During the Proterozoic, this motion was not random. It was choreographed into a slow, immense dance. The Cretons, those ancient roots of continents, began to gather, drift apart, and gather again, weaving patterns that would echo across billions of years. The first act of this continental ballet was the formation of Columbia, sometimes called Nuna. Around 1.8 billion years ago, scattered landmasses collided, suturing themselves together with belts of mountains. Imagine a map of Earth where the continents are stitched into a single sprawling landform, stretching across the planet like a vast puzzle solved by fire and pressure. Where seas once divided, mountain chains rose. Where continents ground together, new crust was born, crumpled into ridges that towered above barren plains. Mainstream geology tells us this story through paleomagnetism, the faint signals left by ancient magnetic fields locked into iron-bearing rocks. By measuring the direction of those signals, scientists trace the drift of continents like detectives following faded footprints. They see Columbia as Earth's first true supercontinent, a grand experiment in scale, and though it eventually fractured, it left behind scars still visible in modern landscapes, ancient mountain belts, mineral veins, and craton edges. After Columbia's breakup, the dance continued. The Cretons drifted once more, pulled by the restless currents of mantle convection. Around 1 billion years ago, they reunited in a new embrace, forming Rodinia. This was not merely a continent, but a supercontinent of staggering proportions. Picture it, nearly all the world's land gathered into one colossal mass, ringed by a single global ocean. Speculatively, one wonders what the Earth looked like under Rodinia's dominion. To stand on its shores would be to gaze across endless horizons of barren stone, unbroken by the lush forests or fields we know today. Perhaps microbial mats clung to the tidal flats, their sticky layers capturing grains of sediment, quietly writing their presence into the geological record. The skies above might have been tinted with strange hues, shifting as oxygen slowly crept into the air. But with such vastness came consequences. Supercontinents alter climate on a planetary scale. By clustering land into one mass, Rodinia may have disrupted ocean currents, changing the way heat moved across the globe. Some scientists argue this disruption played a role in plunging Earth into one of its greatest crises, the snowball Earth glaciations that would later lock the planet in ice. In this way, the dance of continents was not just a silent drift, but a movement with consequences for life itself. Geologists piece together this puzzle with fragments. Rocks in Greenland that once pressed against Canada, mineral belts in China that matched those in Australia, signatures of ancient collisions hidden beneath deserts and forests. Each fragment is like a note from a lost score, hinting at the symphony of plates moving in deep time. Yet beyond the facts lies awe. Imagine continents, each the size of modern nations combined, drifting like rafts on an invisible sea of molten rock. Their collisions would have been slow, but relentless, shaping mountains that stretched for thousands of kilometers. Their separations opened oceans where none had existed, birthing new coastlines and shallow seas where microbes thrived. The Proterozoic was not only an age of life learning to breathe, but of Earth learning to move with rhythm. The Cretaceous that had once stood alone now waltzed together, building and breaking bonds in a cycle that continues to this day. Every mountain you see, every coastline you walk, is part of that ancient dance, still ongoing, still rewriting the map of our world. And so, the stage was set, not only for continents to gather, but for fire and stone to shape their edges in spectacular ways. Next came mountains that scraped the heavens and volcanoes that painted skies red. If continents are the dancers of deep time, then mountains and volcanoes are the music, loud, dramatic, and unforgettable. During the Proterozoic, the Earth's surface was alive with such music as cratons collided to form supercontinents. They did not merge quietly. They groaned, crumpled, and pushed upward into vast mountain belts, while molten fires surged from the depths to remind the world that stability is never absolute. Imagine standing at the edge of one of these ancient collisions. Before you, bare stone rises in jagged ridges, new mountains freshly torn from the Earth's crust. There are no trees, no rivers, cascading down green slopes, only raw rock, sharp and young, cutting against the sky. The air smells faintly of sulfur, carried from distant volcanoes that bleed fire into the atmosphere. At night, the glow of eruptions might light the horizon, red against the stars, a reminder that Earth's heart still beat furiously below. Geologists can trace these long-vanished ranges in today's metamorphic belts, zones where rocks were buried, compressed, and transformed. In Canada, the Grenville Eogeny left behind mountains so immense that even their eroded roots stretch for thousands of kilometers. In Africa, ancient belts tell of cratons colliding in struggles that lasted millions of years. These mountains are ghosts now, worn down by time, but in the Proterozoic they were as dramatic as the Himalayas, towers of stone built from patience and collision. Volcanoes, too, were architects of change. Flood basalts poured across vast landscapes, spreading sheets of lava that hardened into dark plains. These eruptions were not fleeting events, but drawn-out spectacles, lasting centuries or longer. They released gases that shaped climates, sometimes warming, sometimes cooling. Carbon dioxide thickened the atmosphere, while sulfur aerosols dimmed the sunlight. Each eruption was a planetary gamble, altering the balance in ways life had to endure. But these fiery upheavals were not only destructive, they were creative. Deep within those volcanic systems, metals and minerals concentrated, leaving behind the ores that humans would one day mine: nickel, copper, gold, and uranium, all hidden gifts forged in the Proterozoic's crucible. In a sense, every electronic device you hold today carries echoes of these ancient fires. Speculatively, one wonders how life responded to such upheaval. Microbes clinging to shorelines may have found themselves buried beneath ash, only to return when new coastlines formed. Hydrothermal systems, heated by magma, may have offered sanctuaries, warm, mineral-rich refuges, where early eukaryotes experimented with complexity. Could it be that Earth's violent reshaping was not merely background noise, but an essential teacher, forcing life to adapt, diversify, and innovate? There is a paradox in mountains. They are born of violence, yet they inspire endurance. The ranges raised in the Proterozoic may be gone to human eyes, but their legacy lives in the strength of Cretaceans, in the mineral veins they left behind, and in the very shape of continents. Without them, the Earth would not look as it does today, and life's path might have wound in different directions. Close your eyes and feel the Proterozoic landscape. Imagine walking across fresh volcanic rock, still warm beneath the surface. Imagine climbing a young mountain, windless and silent, The world spread beneath you in barren majesty. No birds circle the peaks, no forests cover the slopes, yet the sense of permanence is overwhelming. This is the world before life claimed it, raw and untamed. As the Proterozoic unfolded, fire and stone sculpted a foundation for everything to come. The continents were not only joined, they were shaped, refined, and tested by Earth's restless energy. In their shadows, oceans deepened, skies shifted, and the stage was prepared for life's next transformation. The continents were forged, the mountains rose, the volcanoes breathed fire, and now, attention turns to the oceans, where strange waters hid the first whispers of change. When we imagine oceans, we see blue sunlit waves stretching to the horizon, sparkling with clarity. But in the Proterozoic, the seas were not blue. They were alien, painted in hues that would unsettle modern eyes. At times they were green, stained by iron and sulfur. At other times they glowed red, as dissolved iron reacted with the first whispers of oxygen. In the deepest shadows, where chemistry strangled light, the waters may have turned black, dense with minerals and strange compounds. These were not oceans for swimmers or sailors. They were cauldrons, restless and alive with hidden alchemy. For billions of years, Earth's oceans held vast quantities of dissolved iron. The young planet's restless crust spewed metals into seawater, and with no oxygen to bind them, the iron drifted freely, invisible but potent. Then came the cyanobacteria, quietly exhaling oxygen into the air and water. At first, their gift seemed inconsequential, a slow, invisible trickle, but oxygen is a reactive force. The moment it met iron, a great transformation began. Iron oxidized, falling out of solution, sinking like rust into layered sediments. The evidence of this transformation still endures in banded iron formations, or BS. Picture them. Rocks striped in alternating layers of dark iron oxides and lighter silicates formed on the floors of ancient seas. They are the frozen diaries of Earth's changing breath, written line by line across hundreds of millions of years. Each band is a page recording a cycle of abundance and scarcity, of oxygen pulsing and then receding. To geologists, they are more than beautiful rocks. They are testimonies of the moment when Earth's oceans began to change color, chemistry, and destiny. Stand, if only in imagination, on the shore of such a sea. The waves lap against stone, but they carry a strange tint, glowing like liquid garnet under the sun. The smell is metallic, sharp, like rusted iron on a wet day. In the shallows, microbial mats spread across tidal flats, their greenish carpets quietly producing the oxygen that fuels the spectacle. The waters shimmer, but not with clarity. They shimmer with weight, with chemistry in turmoil. It is not a sea we would enter lightly. Mainstream science explains this as chemistry. Oxygen binds to iron, iron precipitates, rocks form, but the speculative wonder lies in scale. This was not an event of years or centuries. It unfolded across eons. The oceans were giant laboratories, each wave a participant in experiments written by physics and biology alike. Imagine the patience of it, the quiet accumulation until whole seabeds were painted in iron, later to be lifted as mountains we now mine for steel. What would it feel like to watch these waters change? Perhaps centuries would pass with no difference at all. Then, in a sudden bloom of microbes, oxygen levels might rise enough to stain the seas red. Entire coastlines could shift hue, an alien spectacle across horizons. Then, as the balance shifted again, the red would fade, returning to darker shades. Life at the microbial scale danced to this rhythm, adapting to swings of chemistry invisible to human senses, but decisive in shaping the planet's future. The oceans of iron and shadow remind us that Earth's past was not gentle, but dramatic. The seas we take for granted, blue, clear, abundant with fish, are recent inventions. For most of history, the oceans were strange, unfriendly, and unpredictable. Yet within them, the foundations of our modern world were forged. The oxygen that turned iron to stone also carved a path for life to grow more complex, to breathe, and eventually to dream. As you let your thoughts drift across these ancient waters, remember, even the sea can change its nature. rewriting itself from iron-rich shadows into a mirror of the sky. And in that rewriting, the future was born. Beneath the tinted waters of the Proterozoic oceans, life was everywhere, and yet it was invisible to the naked eye. No fish darted, no coral reefs grew, no whales sang in the deep. Instead, the seas belonged to microbes, tiny architects of chemistry, masters of survival, and quiet engineers of the planet's destiny. These microbial kingdoms shaped not only the oceans they lived in, but the very air above them. On shallow shorelines, stromatolites rose like low, rocky domes. From a distance they looked like stone, but they were alive. Layer upon layer of cyanobacteria, building mats that trapped sediment, growing upward toward the light. Day by day, these microbial communities exhaled oxygen, releasing a gas they did not need, but which would one day sustain entire biospheres. Imagine walking along such a coast. The shorelines would be crusted with strange knobby mounds, slick and green, their surfaces sticky to the touch, each one a living city, billions of tiny inhabitants working together, reshaping the chemistry of the sea. Deeper in the water, far from sunlight, other microbes ruled. Sulfur bacteria thrived where oxygen could not reach, feeding on chemical gradients, glowing faintly in hydrothermal niches. The deep sea, instead of darkness alone, was alive with microbial activity, ecosystems powered not by sunlight, but by minerals seeping from the Earth's crust. To us, such life seems humble, but in the Proterozoic, this was sophistication itself, cells harvesting energy from rock and water, weaving invisible webs of survival. Mainstream science describes these microbial mats and colonies as simple, as structures, after all, were basic compared to later life. But simplicity is misleading. Within those mats, microbes competed, cooperated, and even exchanged genetic material in ways we are only beginning to understand. They built communities, some thriving in oxygen, others in its absence. This balancing act kept the oceans alive through cycles of feast and famine, ice and fire. In their quiet persistence, microbes invented resilience long before animals or plants ever appeared. Speculatively, one might wonder, what hidden experiments took place in these mats? Did colonies evolve complex behaviors we cannot trace in fossils? Chemical signaling, primitive cooperation, even rudimentary networks of information. If such things existed, they are lost to time, erased without skeletons or shells to preserve them. The oceans may have been alive with complexity. We will never see again a microbial tapestry, now invisible to us except through whispers in the rocks. Close your eyes and imagine descending into a Proterozoic lagoon. The water is murky, tinged green with life. Beneath your feet, the seafloor is carpeted with mats that ripple softly in the current. They release tiny bubbles, oxygen exhaled by unseen mouths. It feels still, yet it is not silent. Every square inch is alive, busy, struggling, changing. You are standing on the very factories of the future. Geologists and biologists today look for traces of these microbial kingdoms in stromatolite fossils and isotopic ratios locked in sediments. The Australian pearlbear, the Canadian shield, and parts of Namibia still hold remnants of these layered microbial archives. They tell us that life in the Proterozoic was not scarce, but abundant, only small. Oceans teemed with life that demanded no eyes, no bones, no symmetry, only persistence. And it is persistence that turned the tide. Over time, the oxygen released by cyanobacteria began to accumulate, rising above the seas, altering not just the chemistry of water, but the atmosphere itself. The microbial kingdoms, with no intent, became planetary engineers. Their invisible breath paved the way for multicellular organisms, for animals, for us. Pause for a moment on that thought. The greatest transformation in Earth's history was driven not by mighty beasts or towering forests, but by the smallest of creatures, working together in colonies no taller than a hand. Their kingdoms ruled for billions of years, unchallenged, unseen, and yet utterly decisive. The Proterozoic seas were kingdoms without kings, realms ruled by mats, cells, and invisible architects. And as these waters slowly cleared, the stage was being set for for a new revolution, for in the depths the murky oceans began to transform, revealing blue horizons and possibilities never seen before. For eons, the Proterozoic seas were heavy with iron and shadow, but change, though slow, is relentless. Oxygen from microbial breath continued to flow into the water, binding with iron, stripping the seas of their metallic hues. Over millions of years, the oceans began to clear. What had once been murky and red turned a purer shade, revealing depths that no human eye would see for billions of years. The transformation of chemistry was also the transformation of possibility. With the iron removed, oxygen had room to accumulate. The oceans, once choked with dissolved metals, became canvases for a new kind of life. Nutrient cycles shifted. Phosphates, once bound and buried, became more available, feeding cells that could grow larger, more complex. The seas were no longer just microbial mats and chemical gradients. They were becoming laboratories for experiments in eukaryotic life. Mainstream science describes this as a revolution in biochemistry, the great oxidation of the oceans. The presence of free oxygen not only allowed for new metabolic pathways, but also created challenges. Oxygen, after all, is both gift and poison. For anaerobic mogoop, it was a toxin that forced retreat into hidden niches, deep sediments or oxygen-starved environments. But for others, it was a spark, a chance to harness new energy systems, to build more ambitious forms of life. Speculatively, one wonders how dramatic these changes looked to life itself. To us, oxygen is invisible, but to microbes, its arrival was a seismic shift. Did colonies collapse overnight, smothered by the very breath of their neighbors? Did others flourish, spreading across newly oxygenated shallows, glowing with vigor in seas that now shimmered with faint clarity? Perhaps entire ecosystems rose and fell on timescales imperceptible to geology, but monumental to the cells living through them. Imagine standing on a Proterozoic shore. As the waters clear, the tides, once greenish and opaque, now reveal hints of depth. Sunlight penetrates further, illuminating mats on the seafloor in ways never possible before. The world has not yet become familiar. There are no fish, no plants waving in the currents. But the ocean is no longer entirely alien. It is becoming a place where complexity can take root. Within these clearer waters, the first true eukaryotic cells emerged, larger than bacteria, with internal compartments and nuclei. They were the prototypes of all complex life. In these tiny vessels, DNA could be stored and protected, energy could be harnessed more efficiently, and cooperation between organelles opened the door to multicellularity. They were still fragile, still microscopic, but they carried within them the seeds of forests, animals, and humanity itself. Geological records show us this transformation through subtle clues, shifts in carbon isotopes, traces of phosphorus cycles, and fossil biomarkers, hinting at the rise of eukaryotes. The evidence is scattered, fragile, but compelling. It tells us that, by the late Proterozoic, the oceans were no longer only bacterial realms. They were nurseries of potential, incubators of the complex. Speculative awe arises when we consider the contingency of it all. If oxygen had not risen, if iron had continued to dominate, would eukaryotes have found their chance, or would life have remained forever microbial? An endless age of mats and films without eyes, wings, or voices. The clearing of the oceans was more than a chemical event. It was the opening of a door, a passage into a new future. As the Proterozoic seas shifted from iron-laden shadow to oxygen-rich clarity, they wrote the prelude to life as we know it. And from these newly blue horizons, Earth's story tilted toward complexity, setting the stage for organisms that would one day walk, swim, and dream. There was a time when the air itself was alien. To breathe it, if we could have, would have been to inhale suffocation. For nearly 2 billion years, Earth's skies were void of oxygen, filled instead with methane, carbon dioxide, and nitrogen. The oceans below, dark with iron and sulfur, mirrored that lifeless sky. And then, slowly, invisibly, the change began. Tiny organisms, Cyanobacteria, clinging to tidal flats and shallow seas, exhaled a new molecule, oxygen. At first, the oxygen disappeared as quickly as it formed. It bound with iron in the seas, staining waters red and leaving behind banded iron formations, big layered journals of chemistry. But eventually, iron became saturated, and oxygen lingered. Molecule by molecule, it began to collect. The Great Oxidation Event, about 2.4 billion years ago, was not a sudden spark, but a long inhale, a breath that filled the planet over millions of years. Mainstream geology finds its evidence in subtle traces. Sulfur isotopes, once varied in the absence of oxygen, suddenly shifted, signaling that oxygen had altered atmospheric chemistry. Rocks turned red with hematite, red beds that could only form in an oxygen-rich world. In these clues, we see the planet's lungs expanding for the first time, a world learning to breathe. But oxygen was no simple gift. For the microbial kingdoms that had thrived in its absence, it was poison. Entire lineages of anaerobes faced extinction, forced to retreat into oxygen-free niches. Deep sediments, underground aquifers, hydrothermal vents, imagine microbial empires, unchallenged for billions of years, collapsing beneath the invisible tide of a gas they could not endure. What we call progress was, for them, apocalypse. Here lies the paradox. Oxygen was both death and opportunity. For some, it erased existence. For others, it offered energy, far richer than any pathway before. With oxygen, cells could extract far more from food, fueling growth and complexity. The same molecule that choked old life gave new life its wings. It was at once a weapon and a tool, a catastrophe and a genesis. Speculatively, one wonders what it felt like for the Earth itself. Did the skies grow subtly brighter as methane was replaced and greenhouse balance shifted? Did the seas sparkle differently under the sun, less opaque, more open to light? To imagine standing there is to see a world on the brink of transformation, though none of its living architects knew what they were building. The Great Oxidation Event is remembered not as a moment, but as a turning point. It reshaped not only biology, but climate itself. Methane, a potent greenhouse gas, dwindled in oxygen's presence, and with its loss came the planet's first great ice ages, frozen equators, glacial seas. Oxygen's breath cooled as well as empowered. The planet gasped, and in that gasp, both beauty and terror unfolded. To this day, we carry oxygen's duality within us. Every breath we take is a reminder of that revolution. The air that fuels our cells is the same air that once toppled entire microbial empires. It is a legacy of survival and change, a story written not in grand creatures, but in the invisible work of microbes. As you reflect on this ancient breath, let the paradox settle. Progress is never pure. The gift of life often comes wrapped in loss. The oxygen that fills your lungs tonight is the same force that swept across the Proterozoic world, reshaping land, ocean, and sky. The world was no longer silent. The earth had inhaled, and nothing would ever be the same. The rise of oxygen is often told as a triumph, a gift that opened the way for complex life. But for much of the Earth's living world, it was a catastrophe. To the anaerobic microbes that had ruled the planet for billions of years, oxygen was not breath, it was poison. Imagine the oceans of the Proterozoic thick with microbial mats and invisible empires. These organisms had never known oxygen. Their metabolisms thrived on a chemistry we would now find alien, drawing energy from methane, sulfur, or simple fermentation. For them, oxygen was corrosive, a molecule that ripped apart delicate pathways and left them unable to survive. As cyanobacteria exhaled oxygen into the seas, the very substance of their world turned against them. It was not a single day, nor even a single millennium of change. It was a slow suffocation. Oxygen seeped into waters once free of it, creeping like an unseen invader. Whole lineages began to collapse. Mats that had flourished for eons withered as oxygen levels tipped too high. Anaerobic kingdoms shrank, withdrawing into the shadows of deep sediments, hidden aquifers, and hydrothermal vents where oxygen could not reach. Picture the silence of that extinction. No bones, no fossils to mark the loss, only absences, fewer chemical traces in the rocks, fewer signals of anaerobic metabolisms. For billions of years, they had been the dominant rulers of the planet, invisible but absolute, and then swept aside by a gas that to us feels like life itself. In their place came emptiness, and then, slowly, new pioneers who could endure the rising tide of oxygen. Mainstream science finds clues to this great collapse in the record of isotopes. Sulfur and carbon signatures shift, showing a reduction in the dominance of anaerobic processes. The chemical story matches the imagined one. Oxygen did not simply appear. It conquered. It erased vast ecosystems without ever needing to strike a blow. Speculatively, we might ask, what did the Earth feel like in those ages of microbial death? Did the oceans change in character as their ancient rulers vanished? Perhaps they grew clearer, quieter, emptier, before being recolonized by oxygen-tolerant successors. Perhaps methane hazes in the sky faded, replaced by crisper blue horizons. And perhaps in ways we cannot yet trace, the extinction of anaerobes reshaped not only chemistry but the planet's mood, shifting Earth from a shadowed, heavy place into one more open, more luminous. The paradox is stark. The very oxygen that choked ancient life created the stage for new life to flourish, but the cost was staggering. An entire biosphere overturned, billions of years of microbial history erased with little evidence left behind. Was Earth's first mass extinction long before trilobites, dinosaurs, or mammals, a purge that reset the rules of survival. There is an echo of this in our own time. Today, human activity is altering Earth's atmosphere again, not with oxygen, but with carbon dioxide and other greenhouse gases. Just as microbes once transformed the world without intent, we now transform it knowingly. Then, as now, the planet responded not in decades, but in sweeping, global shifts. The Proterozoic reminds us that Earth is sensitive, that the chemistry of its air and seas is never permanent, and that life must bend or vanish when change arrives. Close your eyes and imagine those vanishing kingdoms, the mats retracting into deeper layers, the anaerobic microbes hiding in cracks and vents, clinging to survival as the oxygen-rich world grew hostile above them. It is a haunting image. Worlds within worlds, lost not because of weakness, but because of a fundamental incompatibility with the new order. Their fall was not failure, it was inevitability. Yet even in that silence, Earth did not mourn. It simply changed. The old gave way to the new, and oxygen's empire expanded. The planet had chosen a path, or perhaps the microbes had chosen it for the planet. Life would never again be what it had been before. And in that purge, opportunity emerged, for in the ashes of one biosphere, another was waiting to take root, larger, stronger, and forever transformed by the breath of oxygen. From catastrophe, creation often follows. Oxygen, which poisoned and erased so many ancient lineages, also unlocked possibilities never before imagined. In the wake of the Great Oxidation, new kinds of life began to emerge. Cells that did not merely endure oxygen, but embraced it. With that embrace came complexity, and with complexity, the seeds of all future life. Oxygen offered something extraordinary. Energy, compared to the ancient anaerobic pathways. Aerobic respiration unleashed a flood of power. A single molecule of glucose yielded not just a trickle of energy, but a torrent, enough to fuel larger, more sophisticated cells. Suddenly, life had more to spend on building structures, on maintaining complexity, on exploring possibilities beyond the microscopic simplicity that had dominated for billions of years. It was during this time that a profound evolutionary partnership occurred. One cell engulfed another, and instead of digestion, they formed an alliance. The smaller cell became the mitochondria, a powerhouse of energy production, while the larger cell provided protection and resources. This act of symbiosis, known as endosymbiosis, was not merely an accident, it was a revolution. It gave rise to the eukaryotes, organisms with nuclei, organelles, and the ability to grow larger and more diverse than anything before. Mainstream biology tells us this story through genetic evidence. Mitochondria have their own DNA, distinct from the cells that host them, evidence of their ancient independence. This partnership, oxygen, was no longer a threat. It was the fuel for a new level of existence. Without it, complexity as we know it could never have arisen. Speculatively, we might ask, how many times did this attempt fail before it succeeded? Did countless cells engulf others only to collapse, poisoned by oxygen's fire? Was there a moment almost lost to chance, when one pairing endured, and from that fragile union, all plants, animals, and humans would one day descend? The thought is dizzying. The entirety of our history balanced on a microbial gamble that could easily have gone another way. As oxygen spread through the oceans and skies, eukaryotes began to thrive. They did not dominate at once, but they endured, quietly shaping the future. In their nuclei, DNA could be stored and organized, allowing more complex instructions for life. In their cytoplasm, organelles worked together like a miniature city, each part specialized, each contributing to survival. These were no longer solitary actors, they were collectives, organisms within organisms, thriving through cooperation. Imagine peering into a droplet of Proterozoic water under a lens of speculation. Among the familiar bacteria, something larger drifts, a cell with compartments, a nucleus glimmering faintly with potential. It moves differently, grows differently, carries within its possibilities the world has never seen. Invisible to the naked eye, yet monumental in its importance, it is the ancestor of every oak tree, every bird, every human. The great oxidation was not simply a shift in chemistry. It was the ignition of complexity. From poison came power. From extinction came invention. The microbial kingdoms that learned to wield oxygen transformed the stage of life, turning Earth into a place capable of supporting the extraordinary diversity that would one day walk its surface. And yet, the story was far from over. Oxygen's rise cooled the planet, altering climates, driving glaciers across the equator, and challenging life once again. The world had breathed in, but the cost of that breath was a frozen silence, an age of ice that tested everything life had achieved so far. Imagine standing at the equator and seeing not jungles, not deserts, but ice, a world where every horizon glitters white, where the oceans are locked beneath frozen sheets, and where the winds howl across continents, buried in frost. This was Earth, hundreds of millions of years ago, during an episode so extreme that scientists call it Snowball Earth. The hypothesis suggests that glaciers once crept not just from the poles, but all the way to the tropics, sealing the planet in an icy shell. The seas were covered by ice tens or even hundreds of meters thick. Continents once warm with rivers and tides lay silent beneath grinding glaciers. The equator itself, today a belt of heat and rain, was wrapped in white silence, reflecting sunlight back into space and deepening the cold. Geological evidence whispers of this improbable world. In Namibia and Canada, in Australia and Brazil, scientists find ancient glacial deposits in rocks that once lay in tropical latitudes, dropstones, large boulders carried by glaciers, dropped into fine marine sediments, sit as proof that icebergs once floated in seas where today palm trees sway. Layers of cap carbonates rest above these deposits, chemical fingerprints of a planet thawing after unimaginable cold. These rocks are the archives, the frozen diary of Earth's most extreme winter. Mainstream geology explains Snowball Earth as a cascade. As oxygen rose, methane, a greenhouse gas, diminished, stripping the planet of warmth. With less greenhouse blanket, ice advanced. Ice reflects sunlight, cooling the Earth further, creating a runaway effect, until the oceans themselves were entombed. What began as a chill became a global freeze. But step back from the science and imagine the spectacle. To stand on that frozen equator would be to inhabit a dreamlike world. The sky pale, the sun dimmed by reflection, waves gone, seas muffled under their icy lid. Perhaps you'd hear only the crack of glaciers shifting, the groan of frozen rivers pressing against continents. It was not a place for forests or animals. None existed yet. It was a silence deeper than silence, a planet in stillness. Speculatively, one might ask, did the Earth look lonely in that time? Did the stars above shine brighter over a white planet, unbroken by oceans or fields, to microbes hidden in cracks and vents? The surface must have been unreachable, alien, forbidden. For millions of years, life could not spread across open seas or warm shallows. It was forced to endure in refuges beneath ice waiting for a thaw. And yet, even in this frozen age, the story of Earth continued. Volcanoes rumbled beneath glaciers, releasing gases that slowly gathered in the sky. Heat still rose from the planet's heart, unseen but persistent. The snowball was not forever, but for that long pause, Earth existed as a mirror to the cosmos, white, cold, still, and beautiful in its silence. Snowball Earth reminds us of the planet's extremes. The world we know, blue, green, vibrant, is only one face among many. Long before animals, long before forests, Earth was capable of shutting itself into an icy cocoon, reshaping oceans and skies. The evidence lies in stone, but the ore lies in imagining it. A frozen equator, a white horizon, a silence vast enough to hold an entire planet still. Even as the planet lay entombed in ice, Earth's heart did not stop beating. Beneath the frozen skin of Snowball Earth, fire still moved, silent but relentless. Volcanoes smoldered, magma rose, and hydrothermal vents continued to exhale their chemical warmth into black oceans, hidden beneath kilometers of ice. The surface world may have seemed dead, but deep below, the planet's lifeblood pulsed. Imagine standing at the edge of one of these buried volcanoes. Above, the sky is pale and frozen, but here, fire breaks through ice. A volcano erupts, its heat melting local seas, creating pockets of liquid water beneath the frozen lid. Steam billows into air so cold, it crystallizes almost instantly, forming clouds of ice that fall back as frozen snow. These eruptions were not frequent spectacles, but their persistence was enough to change the balance of Earth's atmosphere, one plume at a time. The secret lay in carbon dioxide. Every eruption released it, a gas invisible but potent. Normally, the Earth's carbon cycle balances. Volcanoes emit CO2 and weathering rocks draw it back. But with oceans sealed under ice, rainfall nearly stopped. Weathering slowed, carbon dioxide could not be drawn down as before. Instead, it built up in the air, molecule by molecule, decade by decade, a slow, invisible pressure pucker building toward change. Meanwhile, life clung on in the strangest of places. Hydrothermal vents on the seafloor created oases of warmth, rich with minerals. Here, microbial communities endured, feeding on chemical gradients and heat in lakes trapped beneath ice sheets, like modern Lake Vostok in Antarctica. Microbes may have survived in isolation for millions of years. Shallow waters under thinner ice could have allowed photosynthetic life to persist, faint light filtering through translucent sheets, enough for cyanobacteria to continue their long labor of oxygen production. Speculatively, one wonders about the resilience of this hidden life. Did mats of microbes glow faintly under icy skylights, continuing to weave oxygen into a world that appeared frozen still? Did strange chemistries arise in isolated refuges? Experiments that never spread because the world outside was sealed. Perhaps entire lineages lived and died in secret, erased without fossils, known only to the memory of DNA fragments lost to time. Geological clues support this persistence. Certain isotopic signatures suggest that photosynthesis never entirely ceased during Snowball Earth. Stromatolite fossils continue across the record, hinting that microbial mats endured. Life did not thrive, but it endured, adapting to niches where fire and water conspired to keep the cold at bay. Mainstream science frames this period as resilience under pressure. The surface world may have been silent, but Earth's engines beneath the crust never rested. Subglacial volcanism, mid-ocean ridges, and vents kept water circulating, gases rising, and the atmosphere changing. Over millions of years, the buildup of greenhouse gases reached a tipping point. Eventually, the very fire that smoldered beneath the ice would become the key to Earth's release. Yet, in reflection, this paradox stands out. A planet that seemed utterly inhospitable was, in truth, alive with hidden activity. The frozen silence above was only half the story. Below, fire and microbes coexisted, weaving survival out of extremes. Snowball Earth was not only a catastrophe, it was a crucible, testing life's endurance and proving that even under the harshest conditions, survival finds a way. Close your eyes and imagine being a witness. You are deep beneath the ice, beside a hydrothermal vent. Around you, water glows with heat, shimmering in mineral-rich plumes. Microbes drift in the currents, clinging to survival in a world no larger than their vent field. Above, kilometers of ice press down, shutting out light and air, yet in this darkness, life does not despair. It persists, and in persisting, it prepares for the thaw to come. Snowball Earth was not forever. Fire beneath the ice was patient, but relentless. Its gases would accumulate, its warmth would build, and eventually the planet's frozen grip would weaken. And when the thaw came, it was not gentle. It was a planetary awakening, a surge of storm and flood that reshaped oceans and skies. For millions of years, Earth lay silent under its icy shell, yet the fire beneath never ceased, and the atmosphere above slowly filled with carbon dioxide. Each volcanic eruption released another breath of gas, invisible and unstoppable, until the air itself became a greenhouse of extraordinary power. Then, after tens of millions of years of frozen stillness, the balance tipped. The great thaw began. Imagine the first cracks forming. At the equator, glaciers that had stretched across continents began to fracture. Dark streaks of meltwater snaked through white fields of ice, absorbing more sunlight, hastening the melt. The reflective shield that had kept Earth locked in cold now betrayed it, letting the sun's warmth in. In geologic time, the thaw was sudden. Within perhaps thousands of years, an instant compared to the deep freeze, the snowball cracked open. The release was dramatic. Oceans, once sealed under thick lids of ice, burst free, waves colliding with the sky for the first time in millions of years. Torrents of meltwater poured into seas, stirring layers long separated, unleashing buried nutrients. Storms raged across a world, relearning how to breathe. The silence of white deserts gave way to floods, winds, and thunder. The earth was not merely thawing, it was roaring back to life. Geological records capture the aftermath. On top of ancient glacial deposits lie layers of capped carbonates, thick bands of limestone and dolostone that formed rapidly when oceans, suddenly rich with carbon dioxide, precipitated minerals. These rocks are markers of the thaw, chemical signatures of a world swinging from frozen silence to greenhouse chaos. They are, in a sense, the scars of a planet that went from one extreme to another. For life, the thaw was both danger and opportunity. Microbes that had endured in hidden refuges now spilled into open seas, feasting on nutrients stirred by the melting. The sudden influx of phosphates and iron may have fueled blooms, surges of productivity that changed the balance of ecosystems. Some scientists speculate that these blooms paved the way for evolutionary leaps, creating conditions that encouraged diversity. Speculatively, imagine the spectacle of that rebirth. A world of white dissolving into oceans of stormy blue, thunderheads, building where glaciers had once stretched, tides crashing against cliffs freshly exposed. Perhaps the skies glowed strange colors as greenhouse gases shifted balance, painting sunsets redder, darker, fiercer than before. To witness it would be to watch a planet shedding its skin, awakening from a frozen dream into restless motion. And yet, the thaw was not gentle. Rapid warming may have triggered violent storms, floods, and destabilizations. Oceans may have turned harsh with chemical swings, challenging the very organisms that had survived the freeze. But through this turbulence, life endured, adapted, and perhaps even thrived. The Earth, having tested life with silence, now tested it with chaos. Both extremes were lessened. The Great Thaw was not simply the end of snowball Earth, it was a reset. It recharged nutrient cycles, reshaped climate, and prepared the stage for the next chapters of evolution. From the frozen silence to the roaring storm, the planet proved its dual nature, destroyer and nurturer, prison and cradle. Close your eyes and feel the shift. The crunch of ice underfoot becomes the rush of water. The pale horizon breaks into glittering seas. The stillness of frost gives way to the roar of waves. The earth has awakened, and with that awakening, the story of life is set onto a new, more ambitious path. If you could dive into the oceans of the Proterozoic, you would not see fish, nor corals, nor drifting jellyfish. You would see nothing at all with the naked eye. The waters would appear quiet, barren even, but that silence was an illusion. The seas were alive with invisible empires, vast kingdoms of microbes, bacteria and archaea ruling every tide, every current, every grain of sediment. They built no monuments of stone, they left no cities we could recognize. And yet, they were builders all the same, shaping the chemistry of oceans and skies. Microbial mats stretched across tidal flats like living carpets, layered with billions of cells working in unison. Each layer performed its role. Those on top drank sunlight, exhaling oxygen. Those below fed on sulfides or methane, living in darkness. Together they created bustling, stratified societies, stacked not in towers of glass but in films of slime. From above, these mats looked like strange, knobby mounds or flat crusts along the shore. These are what we now call stromatolites, layered formations that grew as microbes trapped sediments, cementing their presence into stone. Stromatolites are not just fossils, they are monuments of microbial persistence, visible records of invisible empires. Even today, in rare places like Shark Bay in Australia, stromatolites still grow, whispering of an ancient age when they dominated entire coastlines. To shrink yourself down and walk across such a microbial city is to enter another world. Imagine the seafloor not as sand, but as a living pavement, every surface covered in films of activity. The streets are channels of water weaving between colonies. The buildings are layered biofilms, each millimeter thick with bustling communities. Instead of voices, chemical signals carry messages, molecules released to warn of predators, to attract partners, to coordinate survival. The air is replaced by gradients of light and nutrient, shifting as the sun arcs overhead. Here, bacteria and archaea ruled as architects and chemists. Some harvested sunlight through primitive photosynthesis, exhaling oxygen that would eventually reshape the world. Others resisted that oxygen, clinging to ancient ways of life in hidden, anoxic corners. Methane producers, sulfur breathers, iron reducers, all played their part in the ecological symphony. To us, they might seem small, even trivial, but in truth, these microbes were the masters of Earth, more influential than any creature that would follow. Mainstream science shows us their legacy through isotopes and stromatolite fossils. The rise and decline of these formations trace shifts in ocean chemistry, pulses of oxygen, and ecological balances. They are the diaries of microbial history, preserved in stone. By reading them, we glimpse the empires that once dominated, not in grandeur, but in persistence. Speculatively, one might ask, what if we could truly perceive their world as they did? To a microbe, the Proterozoic ocean was not empty. It was crowded, competitive, alive with exchange and danger. Viruses drifted like assassins, preying silently. Predatory microbes lurked, engulfing smaller prey. Colonies rose and fell, competing for light, nutrients, and space. The Proterozoic seas were jungles, not deserts. Only their scale rendered them invisible to our eyes. Yet for all their invisibility, the empires shaped everything. The oxygen in your lungs, The minerals in your bones, even the climate of the skies, all bear their fingerprints. These kingdoms, without monuments, built the world by simply existing, by carrying out their daily struggle of survival. They did not know they were changing the planet, but they did, and their legacy endures in every breath we take. As you drift tonight into the thought of these invisible empires, imagine walking their cities, streets paved with slime, towers of layered mats, signals carried in whispers of chemistry, empires not of marble or steel, but of cells, countless, patient, eternal. The Proterozoic belonged to them, and without their rule, the future could never have come. Empires are never still, not even when they are made of cells, too small to see. In the Proterozoic seas, microbial kingdoms did not simply coexist. They fought. Their battles were silent to our ears, invisible to our eyes, yet they were as decisive as any clash of armies in human history. These were the microscopic wars, fought not with swords or arrows, but with chemistry, competition, and cunning. Bacteria and archaea, the twin lineages of early life, faced off in every tide pool and ocean trench. Both had carved their niches in the primordial world. Archaea thrived in extremes, searing vents, hypersaline lagoons, acidic pools. Bacteria spread across tidal flats, weaving mats and filling shallow seas with oxygen. Each lineage guarded its strategies, but the environment was changing, and oxygen was rewriting the rules. Where once archaea and anaerobes reigned unchallenged, now oxygen-tolerant bacteria advanced into their territories, driving them into corners. Imagine the battlefield at the scale of microns. A colony of cyanobacteria spreads across a rock, exhaling oxygen like an invisible cloud. For oxygen-loving microbes, this is a gift. For anaerobes, it is a toxin, corroding their machinery, forcing them to retreat deeper into the sediment. Layers of biofilms become fortresses, the upper layer producing oxygen, the lower layer defending against it. Each millimeter a border between survival and death. But defense was not always retreat. Microbes also waged war with weapons, chemical toxins crafted to weaken rivals, enzymes that broke apart cell walls, molecules that poisoned metabolic pathways. These were not random excretions, but strategies honed by evolution, as real and ruthless as any blade. Even viruses, those ghostly parasites, prowled as assassins. They infiltrated cells, hijacked their machinery, and burst forth to spread the infection. Whole colonies could collapse under such unseen sieges. Mainstream science traces these struggles through biochemical signatures, genes for antibiotic resistance. Ancient even then, reveal that microbial warfare is not modern, but primordial. The arsenals we use today, antibiotics, antivirals, are echoes of battles fought billions of years ago. The invisible wars of the Proterozoic shaped genomes, forcing adaptation, innovation, and resilience. Speculatively, one wonders about the sophistication of these conflicts. Could microbes coordinate responses, sending chemical signals to warn neighbors of danger? Could colonies act like armies, sacrificing some cells to defend the whole? We know that even today, microbes exchange signals, cooperating in biofilms to resist attacks. It is not hard to imagine that such behaviors, primitive but effective, played out in the Proterozoic seas as well. Close your eyes and imagine walking through one of these microbial cities. Around you, colonies shimmer with chemical colors, invisible in light but palpable in scent and taste. A nearby mat pulses with oxygen, while below it darker layers resist. Suddenly, a wave of chemical toxins floods the street, scattering some colonies, killing others. Viruses drift like unseen predators, striking without warning. To us, this world would feel chaotic, even terrifying, but to the microbes, it was simply life, constant, competitive, relentless. And yet, from these wars came progress. Competition fueled innovation. Those that survived developed new metabolisms, new defenses, new ways to thrive in a changing world. Some learned to tolerate oxygen, others forged alliances, exchanging genes through horizontal transfer. These acts of sharing, born in war, planted the seeds of resilience. The conflicts that seemed destructive were, in truth, engines of adaptation. There is a lesson in these invisible wars, one that echoes into human history. Struggle often gives rise to strength. Entire lineages may fall, but survivors emerge tougher, more adaptable, more capable of reshaping the world. Without the microscopic battles of the Proterozoic, the path to complexity might never have opened. The wars of microbes prepared the way for eukaryotes, for multicellularity, for life as we know it. As you let your mind drift across these ancient seas, remember that empires do not only rise in stone and steel, they rise in films of slime, in layers of cells, in battles fought molecule by molecule. The Proterozoic was not quiet, it was a battlefield, and the victors of those silent wars carried within them the future. Amidst the battles and shifting tides of the Proterozoic oceans, something extraordinary happened. It was not an explosion, not a storm, not even a visible event. It was a quiet accident. One cell engulfed another, and instead of destruction, they formed a partnership. From this fragile alliance came a revolution, one that would change the course of life forever. This is the story of endosymbiosis. A larger host cell swallowed a smaller bacterium, perhaps in an attempt to consume it. But the smaller cell resisted digestion. Instead, it survived inside, offering its host a gift, a new way to harness oxygen's power. The engulfed bacterium became the mitochondrion, the powerhouse of the cell, turning oxygen into energy far more efficiently than any cell had done before. What began as predator and prey became partners, and together they gave rise to the first true eukaryotes. Mainstream biology provides compelling evidence for this revolution. Mitochondria still carry their own DNA, separate from the nucleus, a remnant of their once independent life. They are enclosed by double membranes, scars of engulfment. Their genetic codes bear closer kinship to bacteria than to their host cells. Every eukaryotic organism alive today, from yeast to trees to humans, carries this legacy in every cell. But beyond the science lies the awe. This was not a slow adaptation, but a leap, a moment of cooperation that opened doors no single cell could have managed alone. With mitochondria, cells had access to orders of magnitude more energy. That energy could be spent on building larger bodies, protecting DNA in nuclei, developing complex internal systems. The partnership was the spark that lit the fire of complexity. Speculatively, we might ask, how many times did this experiment fail before it succeeded? Perhaps countless engulfments ended in digestion, with no partnership formed. Perhaps many early alliances collapsed, the partners incompatible. Somewhere, in one cell, the balance tipped toward survival. That one chance union endured, and from it flowed forests, oceans of fish, the beating of hearts, the firing of neurons. Without that accident, complexity, as we know it, might never have been born. Imagine shrinking down and peering into a Proterozoic drop of water at the moment of revolution. Among the ordinary prokaryotes, you see something different. A larger cell holding within it a smaller one, and instead of dying, both thrive. The host grows stronger, dividing with newfound vigor. Its descendants spread, slowly but surely, until they are no longer rare, though invisible to the wider ocean. The future has just been rewritten. The symbiotic revolution did not erase bacteria or archaea. They continued to rule in numbers, in resilience, in diversity. But eukaryotes now carried potential far beyond size. Their complexity allowed them to coordinate, to diversify, to one day become multicellular. In their nuclei, DNA could be managed with precision, allowing genomes to expand. In their cytoplasm, organelles worked in concert, miniature societies within a single cell. These were not mere microbes. They were the prototypes of animals, plants, fungi, and all complex life to come. There is poetry in the fact that cooperation, not competition, birthed this leap in a world dominated by microscopic wars. One act of tolerance changed everything. Two rivals became one organism, and their partnership proved more powerful than any weapon. The lesson echoes through deep time. Survival is not only about struggle, it is also about union. As you let this thought settle, consider your own breath. Every inhale you take fuels mitochondria in your cells, descendants of that ancient partnership. You are, in a very real sense, a community, one body composed of many histories, one organism born of ancient cooperation. The symbiotic revolution lives on in you. The Proterozoic oceans may have looked empty, but in their depths, invisible empires fought, allied, and transformed, and from that world of microbes came the blueprint for everything that would follow. For billions of years, Earth belonged to single cells. Oceans brimmed with bacteria and archaea, their invisible empires shaping air and sea. But around 1.6 billion years ago, something new and fragile stirred, an experiment in togetherness. For the first time, cells began to join, to live not as solitary beings, but as colonies, cooperating in ways that hinted at futures unimaginable. One of the earliest fossils of this transition is called Bangiomorpha, a form of red algae discovered in Canada's Arctic rocks. To the eye, it looks like nothing more than filaments pressed into stone, simple thread-like structures. Yet these tiny imprints hold monumental meaning. They represent the first clear evidence of multicellularity, cells organized into coordinated bodies, growing and reproducing with a unity unknown to their solitary ancestors. Why come together for a cell? Joining others offered both strength and vulnerability. Alone, a single cell could drift unseen, feeding quietly. But united, colonies could grow larger, spreading across tidal flats, catching more light, resisting currents. Together, they had resilience, a greater chance of withstanding the planet's shifting conditions. Yet unity carried risks. A colony required coordination. Cells had to divide labor, to sacrifice autonomy for the survival of the whole. If one failed, the group could falter. Imagine peering into a Proterozoic tidal pool. The water is shallow, tinted with green and brown. On the stones, mats of microbes spread as they always had. But here and there, something different catches the light. Slender threads of algae, fragile but distinct. Each filament is not a single being, but many cells bound together, whispering chemically to one another, choosing cooperation over solitude. They cling to rocks as the tide recedes, determined not to vanish with the waves. Mainstream biology views multicellularity as a series of steps, not a sudden leap. Cells first formed loose colonies, then coordinated divisions, and eventually specialized into different roles. Bangiomorpha may have even practiced sexual reproduction, mixing genes between individuals, a new innovation in the history of life. This meant greater diversity, greater flexibility, and more resilience against the challenges of the environment. For such small organisms, it was an extraordinary risk, but also an extraordinary opportunity. Speculatively, one might wonder how many attempts at multicellularity failed. Did countless lineages experiment with togetherness, only to collapse back into solitary existence? Did fragile colonies fall apart with the tides, leaving no trace behind? Perhaps the fossil record shows only the victors, the rare lineages whose cooperation endured long enough to leave an imprint in stone. The oceans of the Proterozoic may have been filled with brief, fragile unions, invisible to time. There is poetry in their persistence. To imagine these first colonies is to imagine pioneers, fragile bodies, clinging to survival in a world not yet ready to support them. They were not grand forests or towering reefs, but delicate filaments, resilient against odds. They did not roar onto the stage of life, but whispered quietly, altering the possibilities of the future. Today, every tree, every whale, every human being is a descendant of those fragile beginnings. Our bodies are vast collectives of cells, cooperating in intricate harmony, all tracing their ancestry back to those first experiments in togetherness. The risks of unity proved worthwhile. The advantages outweighed the dangers, and from that fragile choice arose the promise of complexity. As you reflect on these beginnings, imagine standing at the edge of that Proterozoic shore. The air is thin, the sea is strange, And on the rocks before you cling colonies so small, they seem almost invisible, yet within them lies the future, the forests, the animals, the world itself, fragile, yes, but determined, and in their quiet resilience, life was already dreaming of what it might one day become. The first multicellular organisms were not masters of their world. They were fragile experiments, testing what it meant to live together rather than alone. Once the door to cooperation opened, evolution began to explore every possible shape and strategy. The Proterozoic seas became a laboratory, and life itself became the experimenter. Some organisms grew as filaments, simple chains of cells, linked end to end, like beads on a string. These filaments floated in shallow waters, each cell performing its task, dividing in rhythm with the others. Strength came from numbers, resilience from connection. If one broke free, the filament could continue, though slightly diminished. These were not yet bodies, as we know them, but they were more than solitude. Others formed sheets, spreading like living carpets across rocks and sediments. Each cell touched its neighbor, forming a united front against currents and waves. Sheets allowed cells to share resources more efficiently, to protect one another, to resist being swept away. They resembled the microbial mats that had dominated for eons, but with new coordination, new whispers of complexity. Still others tried colonial spheres, cells bound in clusters, floating through the water like tiny globes. Inside the clusters, some cells began to take on different roles. A few specialized in reproduction, while others handled growth or defense. It was the faintest shadow of tissues, the earliest hints of division of labor. These were experiments in hierarchy, in unity, in the idea that not every cell needed to be identical to survive. The fossil record captures glimpses of these early trials. Microscopic impressions of filaments, clusters, and mats appear in rocks dating back more than 1 billion years. Chemical biomarkers hint at lineages testing complexity, even when their bodies left no lasting shapes. Banyomorpha, with its thread-like structures and possible sexual reproduction, is one such example. Rupenia, a coiled fossil over 1 billion years old, may represent another. Each of these fossils is like a sketch, an early draft of multicellularity preserved in stone. Mainstream science interprets these as steps in a long, patient process. Evolution does not leap without foundations. It builds slowly, layer by layer, through trial and error. Many of these early experiments did not last. Their lineages vanished, erased by time, leaving only fossils and fragments. But some succeeded, and their success changed everything. Speculatively, one wonders about the forms that failed. Were there strange, soft-bodied colonies that flourished for a time, drifting in shallow lagoons, only to vanish forever? Did organisms arise that left no mineralized record, their bodies too delicate to survive the weight of eons? Perhaps the oceans of the Proterozoic were filled with a diversity of experimental forms we will never know, each a story untold. Evolution is a tinkerer, not a planner. It builds, it tests, it discards, and the oceans were its workshop. Imagine watching this world unfold. In one tidal pool, filaments of algae sway gently, capturing light. In another, spherical colonies drift like microscopic lanterns, each glowing faintly with potential. On a rock, sheet-like colonies cling, layered in cooperation. None of these forms look impressive to the human eye, but together they represent a profound shift. The recognition, written in biology, that life could be more than one. There is beauty in the fact that complexity did not appear in a single stroke, but in a chorus of attempts. Each experiment carried lessons. Some lineages showed that size could resist predation. Others revealed that specialization could increase efficiency. Still others hinted at reproduction as a shared duty, not an individual burden. Each trial built toward futures unseen, shaping the possibilities of evolution. And though many experiments failed, their echoes remain in us. Filaments live on in algae, sheets in fungi, colonial spheres in certain protists. We are the inheritors of their persistence, the living proof that cooperation, once tested, could endure. As you let your thoughts drift tonight, picture the Proterozoic oceans as a stage of endless rehearsals. Life was trying on costumes, testing scripts, discarding what did not work. From those fragile performances came the beginnings of a play that would last for billions of years. The experiments in form were not just biology. They were the opening lines of complexity's story. Multicellularity began as fragile filaments, sheets, and clusters, but its promise stretched far beyond those humble beginnings. Once cells learned to live together, the door to new possibilities stood open. Cooperation allowed for more than size. It allowed for specialization. No longer did every cell need to do everything. Some could take on defense, some reproduction, some energy capture. Division of labor gave organisms efficiency, resilience, and the potential to grow beyond the scale of the microscope. This was the great turning point. With cooperation came differentiation, the seed of tissues and organs. Though still primitive in the Proterozoic, these pioneers carried within them the blueprint for forests, reefs, and creatures with hearts and eyes. From red algae clinging to ancient shorelines to simple eukaryotic colonies drifting in shallow seas, they all whispered the same truth. Together, life could reach further than solitude allowed. Mainstream science shows us glimpses of this promise in the fossil record. Filamentous fossils, like Bangiomorpha, and coiled forms like Rupania, are milestones, evidence that multicellularity was not a single invention, but a repeated experiment across lineages. Biomarkers hint that other groups, perhaps early fungi, algae, or protists, were testing similar strategies. Each experiment was a step toward complexity, each survival a confirmation that the idea worked. Speculatively, one wonders what futures might have been lost. Did some colonies edge close to higher complexity, only to vanish in the tides of extinction? Were their entire lineages of multicellular life, diverse and strange, erased without fossils? Forgotten by time, the ocean may have been filled with bodies soft and transient, their promise real but fragile. If so, then the world we know today rests on the rare survivors of countless failed futures. Still, those survivors mattered. By the late Proterozoic, multicellularity was no longer an experiment. It was a trend spreading across multiple kingdoms of life. The implications were profound. Larger bodies could withstand currents, exploit new environments, and store more energy. Sexual reproduction spread diversity, fueling adaptation. Complexity was no longer improbable. It was inevitable. Imagine the shoreline of a Proterozoic sea. The rocks are bare, the air thin, but in the shallows cling delicate threads of algae. They are unremarkable to the eye, fragile in form, yet they carry within them the power to change the planet. If you could see with the vision of time, you would glimpse not only filaments, but the forests and animals that would one day descend from their persistence. It is as if the future itself is wrapped tightly inside those colonies, waiting patiently to unfurl. The promise of multicellularity was not immediate. It would take hundreds of millions of years before animals appeared, before the Cambrian seas exploded with diversity. Yet the foundation was already laid. The Proterozoic pioneers had proven that cooperation worked, that larger bodies could endure, that specialization was possible. Every lineage that followed built on their fragile beginnings. There is poetry in their persistence. The cells that first clung together could not know they were shaping futures. They could not know that forests, reefs, and human minds would arise from their unity. Yet they carried within them that possibility, quietly, stubbornly, patiently. In their smallness lay greatness. In their fragility lay resilience. As you drift on this thought, imagine that shoreline once more. The colonies shimmer in shallow water, barely visible, vulnerable to waves and storms. And yet they endure. They hold tight to rocks, to light, to one another. In that quiet endurance lies the promise of futures, an unbroken thread from algae to oak trees, from filaments to forests, from colonies to consciousness. The earth is not still. Beneath the calm surfaces of seas and lands lies a restless heart, moving continents as if they were rafts adrift on molten tides. In the Proterozoic, this restlessness expressed itself on a scale unlike anything before. Continents gathered, split apart, and gathered again, breathing in cycles that reshaped the planet's face. To walk across Earth then would have been to stride across an unfinished puzzle, its pieces drifting, colliding, and breaking anew. Scientists call this rhythm the supercontinent cycle. Every few 100 million years, the scattered continents of Earth draw together into a single landmass, only to fracture again and begin the long drift toward reunion. During the Proterozoic, this cycle gave us some of the first great landmasses. Columbia, also known as Nuna, and later Rodinia. Each of these supercontinents was vast, stretching across much of the globe, linking regions that today are oceans apart. Imagine Columbia, forming nearly 1.8 billion years ago. Land masses collided, mountain chains rose, and for the first time, Earth bore the scars of continental sutures on a global scale. Then hundreds of millions of years later, as Columbia drifted apart, its fragments slowly reunited to create Rodinia around 1 billion years ago. Picture it, an immense expanse of land, barren and rocky, encircled by a global ocean. To stand upon its shore would be to gaze across horizons of stone stretching endlessly, unbroken by forests or animals. It was not a world of life as we know it, but a stage being prepared for futures unimaginable. The evidence for these ancient continents lies locked in stone. Geologists trace their outlines through paleomagnetism, tiny mineral compasses frozen in rocks, recording the direction of Earth's magnetic field when they formed. By aligning these compasses across the globe, scientists can reconstruct the movements of land long vanished, coupled with clues from mountain belts, mineral veins, and matching rock types found on opposite sides of modern oceans. A picture emerges: continents drifting, colliding, breaking, and drifting again, like the slow inhale and exhale of a planet's breath. Mainstream geology describes these movements in terms of plate tectonics, mantle convection, dragging plates across the surface. But speculatively, one might see it as Earth's heartbeat, a rhythm older than any life, shaping environments and rewriting climates. Each supercontinent altered the planet's oceans and atmosphere, redirecting currents, changing how heat and nutrients flowed. When land clustered together, vast interiors became dry and harsh. When it broke apart, new coastlines flourished, creating shallow seas where microbial mats and early eukaryotes thrived. What would it feel like to stand on Rodinia? No grass beneath your feet, no birds above, no soil rich with life, only rock, wind, and the distant crash of waves against cliffs. The air would taste faintly metallic, thin with oxygen. At night, the stars would blaze over a continent so vast it would take months, even years, to cross on foot if such a journey were possible. It was a land empty of sound, yet filled with potential, its barren surface waiting for the green of future eras. The Proterozoics, supercontinents, remind us that the ground beneath us is not permanent. What feels eternal, mountains, coastlines, continents, is in truth temporary, shifting across spans of time too vast for human imagination. Columbia and Rodinia rose and fell long before Pangaea, long before Gondwana, long before the familiar maps we know. Their existence shows us that Earth's face has been redrawn many times and will be redrawn again. As you drift in thought, picture the Earth breathing, continents gathering in, then exhaling into oceans, then drawing back once more. This was the breath of continents, a rhythm as old as the planet itself, and it continues even now beneath our very feet. Continents do not join quietly. When land masses collide, the Earth groans, crust folds, fractures, and thrusts upward, giving birth to mountains that scrape the sky. In the Proterozoic, as Columbia assembled and Rodinia rose, collisions forged ranges as immense as any Himalayas we know today, though their jagged peaks have long since weathered into rolling hills or flat plains. Their roots remain buried in the bedrock as silent witnesses to ancient violence. Imagine the moment of impact. Two cratons drift together, driven by mantle currents that care nothing for the surface world. The clash is slow, measured in millions of years, but the consequences are vast. Rocks crumple into belts hundreds of kilometers long. Heat and pressure metamorphose them, baking minerals into new forms. Quartz, garnet, and mica shimmering in folds of stone. These metamorphic belts are the fossils of mountains, preserved not in bone but in crystalline scars. Evidence of these titanic encounters endures across the globe. The Grenville orogeny, for example, left behind rocks stretching from modern Canada to Scandinavia, remnants of mountains formed 1 billion years ago during Rodinia's assembly. In Africa, belts like the Namakwa Nettles record similar collisions. These ranges were once as formidable as the Alps or Rockies, yet now only their worn foundations remain, eroded by time's patient hand. To geologists, they are ruins, monuments to a vanished landscape. But even as mountains rose, continents were also preparing to break. No supercontinent is eternal. Beneath the crust, mantle plumes pushed upward, stretching the land until it fractured. Rifting tore Rodinia apart, opening new oceans where once there was stone. Faults split across thousands of kilometers, creating valleys that filled with water, birthing coastlines and shallow seas. These rifts were scars of separation, reminders that Earth's crust is never truly still. Mainstream geology sees this cycle, collision, mountain building, rifting, breakup, as the engine of supercontinents. But speculatively, we might view it as the drama of creation and destruction, a pattern written into the planet's very being. Mountains are born of unity, of land converging, but their grandeur is temporary. Oceans are born of division, of land parting, and they too will one day vanish. Earth is a restless artist, sculpting and erasing landscapes in cycles as steady as breath. These geological dramas influenced more than just stone. Mountains changed weather, altering winds and rainfall. Their erosion poured nutrients into rivers and seas, feeding microbial mats and early algae. Rifting created shallow coastal waters, fertile grounds for eukaryotic life to spread. The very act of continents colliding and breaking apart shaped the stage for life's next chapters, even before animals appeared to walk upon it. Speculatively, one wonders what it would feel like to stand in the midst of such change. To climb a Proterozoic mountain would be to ascend slopes bare of trees, their peaks sharp against a thin sky. To stand in a newborn rift would be to gaze across a vast scar, its edges raw, its floor filling slowly with water. The air would be quiet, save for the cracking of stone and the hiss of volcanic vents. It was a world in flux, a world reshaping itself before life was ready to notice. And yet, these changes were not destructive alone. They were creative. The Grenville Mountains, though eroded, enriched the seas with minerals. The rifts of Rodinia opened habitats that would one day host the Ediacaran biota. Mountains and rifts were not only ruins, they were opportunities, gifts wrapped in violence. As we reflect on these cycles, we see a paradox. The ruins of ancient mountains remind us that grandeur is fleeting, yet from that fleetingness comes renewal. Continents rise, fall, and rise again, and with each cycle, life gains new chances to adapt, expand, and dream. The Proterozoic was not a static canvas. It was a masterpiece in progress, painted with stone, erased and painted again. Mountains, rifts, and ruins. Together they were Earth's signature, the marks of a planet alive with motion. When we think of time, we measure it in years, decades, perhaps centuries. But the Earth moves to a rhythm so vast it dwarfs all human reckoning. The cycle of supercontinents, gathering, breaking, reuniting, unfolds over hundreds of millions of years, like the slow pulse of a sleeping giant. This rhythm has guided the planet's history since the Proterozoic, shaping oceans, mountains, climate, and even life itself. Scientists call it the supercontinent cycle, but it could just as easily be called Earth's heartbeat. Each cycle begins with drifting fragments, solitary continents wandering across the globe. Slowly they converge, drawn together by the invisible pull of mantle convection. They collide, raising mountains, welding cratons into vast land masses. For a time, a supercontinent dominates, a single body of stone stretching across much of the Earth. And then heat gathers below, plumes rise, and the supercontinent cracks apart, scattering its fragments into new ocean. The breath ends, and another begins. In the Proterozoic, this rhythm gave rise to Columbia, then Rodinia. Later, in Earth's younger ages, it produced Pangaea. Each supercontinent altered the planet's face and climate. When land gathered, interiors became arid, and winds carried dust across vast distances. When land broke apart, new coastlines flourished, creating shallow seas that teemed with life. The rhythm was geological, but its consequences were biological. Life's story cannot be separated from the breathing of continents. Evidence for this rhythm lies in ancient rocks. Paleomagnetic records reveal the wanderings of continents, frozen in mineral grains that aligned with Earth's magnetic field when they formed. Mountain belts trace the sutures of collisions, scars where land once joined, rift valleys, and oceanic crust reveal the places where breakups began. Piece by piece, geologists reconstruct the pattern, mapping Earth's long inhalations and exhalations across billions of years. Mainstream science explains the cycle through plate tectonics and mantle convection. But speculatively, we might ask, does Earth remember? Is this rhythm simply mechanics? Or is it a kind of planetary memory, a deep pattern woven into the fabric of the world? Every cycle feels like repetition, that each produces something new, different arrangements of land, different climates, different opportunities for life. Perhaps the rhythm is less a loop than a spiral, always circling, but always climbing toward new outcomes. Imagine standing on Rodinia, knowing nothing of Columbia before it, or Pangaea to come after. To you, the land seems eternal, a single face of stone, stretching to every horizon. Yet in truth, it is only a chapter, destined to fracture, to scatter, to be reborn. The mountains around you are not monuments of permanence, but verses in a song the Earth has been singing since its youth. This rhythm even shapes the planet's climate in profound ways. The clustering of Rodinia may have disrupted ocean currents, reducing heat flow and contributing to the snowball Earth glaciations. The breakup of supercontinents released nutrients into the seas, fueling blooms of life. Climate, geology, and biology moved together, each influenced by the slow breath of the continents. The heartbeat of Earth guided not only stone, but survival. There is humility in this thought. The continents beneath our feet, the maps we know by heart, are temporary. They too will drift, converge, and fracture. Long after us, another supercontinent will rise, its mountains casting shadows over oceans we cannot imagine. And in that landmass, the legacy of today's continents will be preserved in sutures and scars, just as Rodinia's legacy survives in ours. As you rest, let this rhythm settle into your imagination. Earth is not a silent sphere, but a living planet, breathing slowly, patiently, across deep time. Mountains rise and fall, oceans open and close, continents drift and reunite. This is Earth's long rhythm, the heartbeat of stone, steady and eternal, guiding the story of life itself. The seas of the late Proterozoic were not empty. Around 50-75 million years ago, after billions of years of microbial dominance, the ocean floors bloomed with shapes unlike anything the planet had seen before. They were neither plants nor animals in the forms we know. They were soft-bodied enigmas, quilted and fronded, sprawling across shallow seas like a dream given substance. These organisms are known as the Ediacaran biota, named after the Ediacara Hills of Australia, where their fossils were first discovered. Their impressions in stone reveal flat, leaf-like bodies, radial patterns, and intricate quilted textures. Some lay like discs, pressed into the sand. Others rose like fronds, branching delicately, swaying in currents that had never carried fish. Their beauty is haunting, creatures without eyes or mouths, yet thriving in seas that had only just begun to clear and oxygenate. Among the most iconic is Dickinsonia, a creature shaped like a ribbed oval, its surface marked by a quilt of ridges. Some reached more than a meter in length, sprawling across the seabed. Like living carp nearby may have stood Charniodiscus, frond-shaped beings, anchored to the floor, rising into the currents like alien ferns. And then there was Sprigina, a segmented form whose body plan hints at future animals, though its true nature remains uncertain. Together they formed a menagerie of life that looked both alien and strangely familiar, as if glimpsed from another world. Mainstream science still wrestles with their identity. Some researchers interpret Dickensinia as one of the earliest animals, feeding on microbial mats moving slowly across the seafloor. Others see the Ediacaran forms as experiments unrelated to anything alive today, a failed branch of evolution that left no descendants. What we do know is that they were abundant, diverse, and widespread. Their fossils appear not only in Australia, but also in Russia, Namibia, Canada, and beyond, etched into sandstone as ghostly impressions. Speculatively, one might imagine walking across a Proterozoic seafloor. The water is shallow, lit by sunlight. The sand beneath your feet is not barren, but carpeted with quilted ovals, their bodies expanding gently, pulsing with unseen rhythms. Fronds sway around you, tall as saplings, yet boneless, leaf-like bodies drifting in the current. There are no fish darting between them, no predators lurking, only stillness and gentle motion. It is not a reef, not a meadow, but something in between, a garden of alien forms. These creatures were fragile, yet profound. They were the first large-bodied organisms to dominate Earth, the first beings that could be seen without a microscope. After billions of years of invisibility, life had begun to write itself in visible shapes, leaving fossils large enough to fill human hands. The Ediacaran seas were a canvas where life painted its first brushstrokes of size and form. Knowledge nuggets lie in their fossils. Some Dickensinia specimens preserve organic molecules, cholesteroids that suggest animal affinity. Others show faint trails as if the creatures had moved, feeding, or repositioning themselves. These clues are rare, tantalizing, and incomplete. Each fossil is a riddle, offering glimpses but never the full story. Speculatively, perhaps the Ediacaran biota represent Earth's imagination at work, life experimenting with geometry, testing what forms could exist, quilts, fronds, discs, and spirals, as though evolution were sketching ideas before committing to the bolder strokes of the Cambrian explosion. Some of those sketches may have endured, carried forward in animal lineages. Others vanished entirely, erased like dreams upon waking. To picture them is to see Earth in transition, caught between the microbial world and the animal kingdom. The Ediacaran seas were neither empty nor crowded, but filled with beings that defy our categories, creatures whose beauty lies in their mystery. They remind us that life's story is not a straight line, but a tapestry of experiments, many forgotten, some still unfolding. The Ediacaran biota are some of the most haunting fossils in Earth's story. They appear suddenly, thrive for tens of millions of years, and then vanish before the Cambrian explosion. But the greatest mystery is not their disappearance, it is their identity. What were they? Were they the ancestors of animals, the first steps toward the diversity we know today? Or were they evolutionary experiments, entire lineages that flourished briefly and left no descendants? Scientists have debated these questions for decades. Some fossils, like Dickensinia, seem animal-like. Their bodies show signs of growth, expanding in a regulated, patterned way, unlike simple microbial mats. Chemical residues within Dickensinia fossils even contain sterols similar to those in modern animals, suggesting they may have been among the first true animals. Trace fossils' faint grooves in sediment hint that some Ediacaran creatures could move, gliding slowly across the seafloor, feeding on microbial mats. If true, these were the planet's first grazers, reshaping ecosystems by consuming the very carpets that had dominated for billions of years. Other fossils, like the frond-like Charniodiscus, seem harder to place. Some scientists propose they were early animals related to corals or sea pens. Others argue they may not have been animals at all, but a completely separate kingdom of life, now extinct. built on rules we no longer see in biology. The quilted bodies of many Ediacaran organisms, with repeated branching patterns, do not match the body plans of known animals. Were they closer to fungi, giant protists, or something entirely different? A failed experiment in multicellularity that rose and fell before the Cambrian dawn. Speculatively, one might imagine that the Ediacaran seas were filled with both ancestors and experiments, side by side. Perhaps some lineages gave rise to sponges, cnidarians, and eventually more complex animals, while others left no heirs. The seafloor may have been a patchwork of futures, some that endured, others that faded like echoes. The fossil record offers tantalizing but incomplete answers. In Namibia, Russia, and Australia, Ediacaran fossils show impressions of soft bodies pressed into ancient sand. Some display radial symmetry, others bilateral hints, yet most lack clear organs or structures we can compare to modern animals. They are shadows in stone, teasing us with forms but withholding their essence. Mainstream science leans toward the idea that at least some Ediacaran organisms were early animals. Sponges, cnidarians, and biliterians may trace their ancestry to this period, but the diversity of forms suggests that many were evolutionary sidelines, branches cut short before the tree of life fully spread. The Cambrian explosion that followed did not simply arise from nothing. It may have been seeded by Ediacaran experiments, successful or otherwise. Speculatively, it is tempting to see the Ediacaran as Earth's sketchbook. Life, having achieved multicellularity, began testing shapes and strategies: discs, fronds, quilted ovals, segmented forms. Some designs would evolve into enduring lineages, others were abandoned, erased by time. Evolution does not plan, it explores, and the Ediacaran seas may have been filled with possibilities, only a fraction of which would survive. Imagine walking across a shallow Proterozoic seafloor garden. Around you lie quilted mats of Dickensinia, feeding silently. Fronds of Charniodiscus sway above, anchored like alien trees. Strange spiral forms cluster nearby. Some of these organisms will vanish forever, their futures erased. Others may quietly pass down traits that will one day emerge in corals, jellyfish, worms, even us. Yet to your eye, they are all equally mysterious, equally alien, equally fragile. The Ediacaran reminds us of how much of life's story we cannot know. For every fossil preserved, countless organisms vanished without trace. For every lineage that survived, many more ended in silence. Perhaps most of the Ediacaran world is lost, a hidden chapter erased by time's hand. And yet, from that mystery rises awe, life's willingness to experiment, to try forms both familiar and strange, to explore futures even at the risk of failure. Were the Ediacaran creatures our ancestors, or were they evolutionary dreams, fleeting and unfulfilled? The truth may be both. They were the threshold, the first attempt at visible complexity, a chorus of voices singing in different directions. Some voices faded, some lingered, but together they carried life toward the Cambrian dawn. The Ediacaran biota emerged with quiet strangeness, filled the seas with alien beauty, and then vanished. By the dawn of the Cambrian, most of these quilted ovals, frond-like forms, and soft-bodied enigmas were gone, leaving only faint impressions in stone and unanswered questions in their wake. Their disappearance is one of life's great mysteries, a fading act written into the deep past. What caused this vanishing? Scientists offer several possibilities. One is ecological competition. As the Cambrian began, new animals appeared, creatures with mouths, guts, and the ability to move and hunt. For soft-bodied Ediacarans, which lived by absorbing nutrients or grazing passively on microbial mats, this new wave of predators may have been devastating. Once ecosystems became more active, passive forms were pushed aside. Another explanation is changing oxygen levels. The Proterozoic seas had slowly become oxygenated, but not uniformly. If conditions shifted, oxygen dropping in some regions, rising too rapidly in others. The delicate balance the Ediacaran organisms depended on may have been disrupted. Their quilted bodies, adapted to low-energy lifestyles, may not have survived in the faster-paced, oxygen-rich world of the Cambrian. Climate, too, may have played a role. After Snowball Earth and its dramatic thaw, the planet was prone to swings. Shifts in temperature, currents, or nutrient cycles could have reshaped habitats, leaving the Ediacarans stranded. In this sense, they may have been victims of Earth's own restlessness, caught in transitions they could not endure. Speculatively, we might see their disappearance not as a sudden extinction, but as a fading, like mist in the morning sun. Perhaps they dwindled gradually, retreating to fewer habitats as competition rose and environments shifted. Perhaps the last Dickensia clung to a shoreline as new Cambrian animals swam above, their presence unnoticed by creatures that would inherit the seas. If so, then the Ediacaran vanishing was not an abrupt catastrophe, but a quiet passing, a slow erasure from the stage of life. The fossil record offers clues but no certainty. Ediacaran impressions fade around 554 million years ago, replaced by the hard-bodied forms of trilobites, worms, and other Cambrian creatures. It is tempting to see the Cambrian explosion as the killer, but perhaps it was simply the successor, life's next chapter, rising as the old one closed. Speculatively, what if the Ediacarans were not failures, but stepping stones? Perhaps traits they pioneered, large size, modular growth, surface area body plans, echoed into later lineages. Even if their exact forms vanished, their experiments may have seeded ideas for evolution to carry forward. In this sense, they are not lost, but transformed, their legacy hidden in the bodies of creatures that came after. To imagine their final days is to picture a strange twilight, seas still filled with quilted discs, but their numbers thinning, friends swaying, but fewer each year, and in the shadows, new shapes emerging, creatures with shells, with claws, with hunger. The quiet gardens of the Ediacaran gave way to bustling Cambrian reefs, filled with motion, sound, and struggle. The dreamlike stillness dissolved into a world of activity. The vanishing of the Ediacarans is a reminder of how much of life's story lies in absence. What we know of them comes only from their traces, shallow impressions pressed into sandstone, delicate patterns that survived against odds. For every fossil we hold, countless others were lost. For every organism preserved, millions more vanished without a whisper. The Ediacaran world is like a half-remembered dream, strange, beautiful, and gone. As you drift in thought, consider this. Every lineage has its time. Some blaze brightly, some fade quietly, but all leave their mark. The Ediacarans remind us that life's history is not only about survival, but about imagination, about experiments in form and being. Though they vanished, their mystery endures, a soft echo of the deep past that continues to haunt the present. The closing chapters of the Proterozoic were filled with tension, like the quiet before a storm. The seas that had once been ruled by microbial mats and quilted Ediacaran organisms were beginning to change. Oxygen levels, rising slowly over hundreds of millions of years, finally reached thresholds that reshaped ecosystems. The seafloor, once still and dreamlike, was stirring. In these oceans, the last of the Ediacaran forms lingered. Dickensonia, lying like patterned carpets, Charnia discus swaying in currents, soft-bodied enigmas still clinging to their niches. But alongside them appeared something new, signs of motion, traces of creatures burrowing, crawling, and reshaping the sediment. These were not mere impressions of bodies pressed into sand. They were trace fossils, records of behavior. Tiny tunnels, grooves, and networks etched into ancient seafloors reveal the actions of early animals, worms or worm-like beings, moving through sediment, disturbing microbial mats, and creating the first complex benthic ecosystems. Mainstream science calls this the beginning of ecosystem engineering. By borrowing these early animals' oxygenated sediments, changed nutrient cycles, and disrupted the mats that had ruled the seas for eons. What seems like a simple act, digging, was in truth revolutionary. It was the first time creatures reshaped their environment in ways that rippled outward, changing the rules for all who lived there. Speculatively, one might imagine walking across such a seafloor. The quilted ovals of Dickinsenia lie still, but here and there the sand stirs. A faint ripple moves across the sediment as a worm-like creature burrows beneath. Tiny tracks curve away, vanishing into darkness. For the first time, the seafloor is no longer a static canvas. It is a living, shifting landscape, restless and alive with hidden activity. These changes also foreshadowed something greater: the rise of predation. Until now, most life forms absorbed nutrients directly or grazed passively. But traces suggest that some early Cambrian pioneers were beginning to probe, pierce, and consume. With predators came prey. With prey came defenses, and with defenses came innovation. The slow arms race that would define the Cambrian explosion had already begun in these late Proterozoic shadows. Fossils from this transitional time are rare, but powerful. They show burrows winding through sedimentary layers, shallow grooves marking movement across microbial mats, even signs of vertical escape tunnels. Each mark is a sentence in a story that bodies alone cannot tell. The Ediacaran left us its forms. These trace fossils leave us its actions. Together, they reveal a world on the edge of transformation. Speculatively, perhaps the seafloor itself felt different in these final Proterozoic ages. For billions of years, it had been layered calmly, microbial mats spreading across it like quiet quilts. Now those quilts were torn, disrupted by creatures tunneling, feeding, stirring oxygen into their depths. The silence was ending. Life had begun to move with intent. This period was not only biological, but chemical. Oxygen levels in the oceans rose unevenly, creating patches of opportunity where more active metabolisms could thrive. In some places, animals with greater energy needs emerged. In others, the old anaerobic ways still held on. It was a patchwork Earth, with ecosystems side by side, some ancient, some modern. Out of this mosaic, the future of life was about to take shape. The late Proterozoic seas, then, were worlds of contrast. Soft-bodied enigmas from the Ediacaran still lingered, but around them, small restless creatures carved paths, burrowed tunnels, and changed the very fabric of the seabed. These shadows of transition were subtle, but they were decisive. They were the first cracks of light before the Cambrian dawn, the hints that life was preparing to burst into new forms. As you imagine this seafloor, see both worlds at once: the stillness of quilted bodies, the motion of hidden worms, the silence of ages, the stirrings of change. This was the threshold, the last breaths of one era, and the first whispers of the next. When the Ediacaran seas gave way to the early Cambrian, life made a bold decision. It put on armor. For the first time in Earth's history, creatures began to encase themselves in mineralized shells, spines, and plates. These delicate fragments, no larger than a fingernail, mark one of the most profound transitions in evolution. They are known collectively as the small shelly fossils, and though tiny, they represent the first wave of skeletons on Earth. Before this moment, life had been soft. Bodies were quilts, fronds, and films, vulnerable to currents and to the first stirrings of predation. But by around 550 million years ago, something changed. Organisms began pulling minerals from seawater, calcium carbonate, phosphate, silica, and fashioning them into protective coats. Spicules bristled, shells enclosed, scales layered. For the first time, the seas glimmered with hard reflections, tiny sparks of armor on the seafloor. The fossils themselves are fragmentary, often preserved as isolated plates, tubes, or spines. To paleontologists, they look like pieces of a puzzle, with most of the picture missing. Some belonged to early mollusks, perhaps small snail-like creatures. Others were the armor of early sponges or worm-like animals. Still others cannot be matched to any modern group. Their shapes too alien, their functions too obscure. Yet collectively they tell us that evolution had crossed a threshold. The age of skeletons had begun. Why skeletons? Mainstream science points to both defense and opportunity. As predators emerged in the late Proterozoic, soft-bodied organisms faced new dangers. Armor offered protection, At the same time, skeletons provided structure, allowing bodies to grow larger, move differently, and anchor muscles. A shell was not only a shield, it was a framework, a new architecture of life. Speculatively, one might see the invention of skeletons as the beginning of life's arms race. The moment one creature donned armor, others had to respond by evolving stronger jaws, sharper spines, or new strategies of speed and stealth. Each innovation demanded another. The seafloor, once a quiet garden of fronds and quilts, was becoming a battlefield of escalation, driven by the invention of bone-like barriers. Imagine kneeling at a Cambrian shoreline, sifting sand through your fingers. Mixed among the grains are tiny, glimmering fragments, cones, tubes, and scales, once part of creatures that crawled or drifted in these waters. To the naked eye, they are almost invisible, but under magnification they reveal exquisite detail, tiny ridges, spirals, and lattices, each designed with precision by evolution's patient hand. They are the whispers of the first armored lives. Knowledge nuggets lie in their diversity. The small shelly assemblage includes Cloudina, tubular organisms that may have been among the earliest reef builders, clustering together in colonies. It includes spiny fragments thought to belong to early annelids, and mineralized plates that hint at the origins of brachiopods and mollusks. Each fossil is a breadcrumb leading toward the explosion of forms that would soon follow. Speculatively, we might ask, did the appearance of skeletons feel sudden, even to life itself? For billions of years, survival had meant being soft, blending into mats and sediments. Then in what seems like a geological instant, life put on armor, as though the seas had grown dangerous enough to demand it. Was this the moment life first began to imagine war, to shape itself, not only for survival, but for conflict? The small shelly fossils are humble, yet they represent something profound. They are the prototypes of armor, teeth, claws, and bones, the very structures that would define animals for the rest of time. Without them, there would be no trilobites, no fish, no mammals, no os. These fragments are the first drafts of skeletons, written in phosphate and carbonate, carried forward into every body that followed. As you reflect, imagine the world in transition, the soft-bodied Ediacaran gardens fading, the seafloor filling with glittering fragments of shells. Tiny though they were, they marked a shift as great as any in life's history. The Earth was preparing for an explosion of diversity, and the first sparks of that brilliance gleamed in the armor of the small shelly mysteries. The final chapters of the Proterozoic carried with them a sense of anticipation. For billions of years, life had been small, soft, and slow. Then, in the late Ediacaran and earliest Cambrian, whispers of change rippled across the seas. The small shelly fossils gleamed in the sediments. Worms carved burrows through microbial mats, and oxygen levels continued to climb. It was as though the stage was set, the actors assembled, and the curtain about to rise on a drama unlike anything before. This build-up is what scientists call the prelude to the Cambrian explosion. It was not a single event, but a series of thresholds being crossed. Oxygen, once scarce, now approached levels capable of sustaining more active metabolisms. Genetic toolkits, the molecular instructions for building bodies, had grown more sophisticated. Among them were the Hox genes, master regulators that controlled body plans, guiding where limbs, segments, and organs could develop. With such blueprints in place, the possibilities of form multiplied. Mainstream science explains the Cambrian explosion as the convergence of many factors: oxygen thresholds, ecological pressures, genetic innovation, and the escalation of predator-prey dynamics. But speculatively, one might see it as a spark waiting to ignite. For eons, life had experimented: quilts, fronds, colonies, shells. Now the conditions aligned for an outburst of creativity, a burst of diversity so sudden it seems almost marsupial in the fossil record. Imagine standing at the edge of this dawn. The seafloor is no longer quiet. Tiny shelly creatures scuttle, leaving faint tracks. Worms burrow beneath the sand, stirring oxygen into sediments. Soft-bodied forms still linger, but they are no longer alone. Currents carry specules, shells, and fragments, tokens of a new kind of survival. The ocean feels restless, alive with motion and innovation. The fossils from this time whisper of escalation. Predator and prey pushed each other forward in an arms race, armor against teeth, speed against traps, stealth against strength. Each adaptation created new opportunities, new challenges. Ecosystems that had once been stable and slow became dynamic, filled with tension and competition. The ancient stillness was breaking. Speculatively, one might wonder, was the Cambrian explosion inevitable, or was it fragile, a chance confluence of conditions that might never have happened again? If oxygen had risen differently, if genetic toolkits had evolved more slowly, if predators had not emerged, perhaps life would have remained microbial and soft-bodied forever. The seas might still be carpets of mats and quilts, with no eyes to see, no shells to glisten, no creatures to move with purpose. Instead, the edge of the Cambrian carried promise. Within a few million years, trilobites would scuttle across the seafloor, sponges and corals would build reefs, and worms would weave tunnels in layered sediments. Complexity was no longer potential, it was reality. The world was about to awaken in ways no Proterozoic creature could have foreseen. As you reflect, imagine the feeling of that threshold, a silence stretching for billions of years, broken first by whispers, then by songs. The earth, once dominated by invisible empires and fragile fronds, was preparing to erupt with diversity. The dawn of the Cambrian was not just a new chapter, it was a new book written in the language of shells and skeletons, muscles and movement. This was the edge of an explosion, the brink of life's great unveiling. The seas held their breath and then, in a surge of brilliance, exhaled. Beneath the continents of the Proterozoic, the earth was never still. Its crust groaned, cracked, and sometimes tore wide open, releasing fire from the deep. When mantle plumes surged upward, they poured vast floods of lava across the land, creating what geologists call large igneous provinces. These were not small eruptions, but cataclysms. Oceans of molten rock spilling across thousands of square kilometers, reshaping the face of the world in waves of fire. To stand on such a continent would have been to witness a landscape aflame. Rivers of basalt rolled across the horizon, hardening into dark stone that stretched for hundreds of miles. Ash plumes rose into the sky, blotting out sunlight, cooling the planet even as greenhouse gases from the eruption worked in the opposite direction. The climate swung wildly, first into darkness, then into heat. For microbes clinging to shallow seas or mats along shorelines, every eruption was a crisis. One such outpouring is recorded in the Mackenzie Large Igneous Province of Canada, created around 1.27 billion years ago. It is the scar of a volcanic event so immense it dwarfs anything in recorded human history, leaving behind a radiating swarm of dikes and lava flows. Other flood belts in what is now India, China, and Africa tell similar stories, times when the Earth's mantle surged upward, blanketing continents in fire. Mainstream geology reads these provinces as markers of Earth's internal rhythms, mantle plumes rising, plates shifting, supercontinents breaking and reforming. But to life on the surface, they were disasters. Ash choked the skies, acid rain fell on seas, and volcanic gases shifted the balance of atmosphere and ocean chemistry. Yet, through it all, life endured. Microbes retreated into sediments, sheltered in hydrothermal vents, or adapted to the new chemistries carved by eruptions. Speculatively, one might imagine the eerie beauty of such a world. The horizon glows red, the air shimmers with heat, the ground trembles beneath every step. Lava advances slowly, relentlessly, like a tide of molten stone. Beneath the ash-darkened sky, microbial mats lie smothered, only to return in cracks and pools once the land cools. To watch would be to see destruction, but also to see resilience written quietly in the persistence of life. Volcanism shaped not only landscapes, but opportunities. The weathering of fresh basalt released nutrients into the oceans, fueling blooms of algae and microbes once the crises ended. Minerals carried into the seas enriched ecosystems, paving the way for new evolutionary experiments. Out of catastrophe came renewal. The very stones of these provinces became cradles of resource copper, nickel, and other metals concentrated by the heat, still mined by humans today. The paradox of volcanism is clear. It was both destroyer and giver, a force that ended habitats but also created new ones. Entire microbial communities may have been extinguished in one region, only for others to flourish in the fertile aftermath. Life learned to bend, to scatter, to adapt, preparing for future challenges. To this day, we can walk across the ancient basalt plains, their surfaces cracked and weathered, their fires long gone. Yet within those rocks lies the memory of Proterozoic cataclysm, an earth that tested life with fire and a biosphere that answered with endurance. As you reflect, imagine the earth as a restless giant, its breath sometimes fire, its silence sometimes ash, its silence sometimes ash. The Proterozoic was not only an age of still seas and quiet growth, but also of continents aflame. Fire from the deep was both a trial and a teacher, reminding life that survival meant resilience, that even in destruction, there was the possibility of renewal. Not all catastrophes rose from beneath the crust. Some came hurtling from the heavens. Throughout the Proterozoic, Earth was struck by asteroids and comets, celestial visitors that arrived with unimaginable violence. Their impacts scarred the planet, shaped its crust, and tested the resilience of life that clung to its fragile footholds. One of the most famous of these is the Sudbury impact in present-day Ontario, Canada. Around 1.85 billion years ago, a massive asteroid or comet slammed into the Earth, releasing energy greater than millions of nuclear bombs combined. The impact carved out a crater more than 200 kilometers wide, one of the largest confirmed impact structures on our planet. Molten rock flooded the basin, and debris was flung across continents. To stand anywhere near the blast zone would have been to witness a nightmare. Fire raining from the sky, shockwaves leveling landscapes, tsunamis racing across distant seas. The evidence of this cosmic strike remains in the rocks. The Sudbury Basin is ringed with impact fresh, shattered fragments of stone welded together by the force of collision. Vast melt sheets, once oceans of molten rock, cooled into layered formations still visible today. The crater itself has been deformed by later tectonics, but its scars are unmistakable. Even after nearly 2 billion years of erosion, the memory of that moment lingers in stone. Mainstream geology interprets such events not only as destruction, but also as creation. The Sudbury impact concentrated vast deposits of nickel, copper, and precious metals, later mined by humans. Other impacts fractured the crust, altering tectonic patterns, opening basins, and perhaps even influencing the cycles of supercontinents. Catastrophe reshaped geology as much as biology. For life, however, the story was one of trial. Microbes that had persisted through volcanic winters now faced skies turned to fire. Dust and vapor may have dimmed sunlight for months or years, altering photosynthesis. Acid rains would have poured from the sky, oceans churned by shockwaves and tsunamis to fragile microbial mats. These changes were devastation, yet life survived. Buried in sediments, sheltered in hydrothermal vents, or hidden deep underground, microbes endured until conditions calmed. Their resilience was extraordinary. Proof that even cosmic violence could not silence life's persistence. Speculatively, one might imagine the terror of such an event. You stand on a Proterozoic shoreline, watching the horizon. A sudden flare ignites in the sky, brighter than the sun. Moments later, the world shakes, winds roar, and walls of water race toward you. In the distance, forests do not yet exist. Animals have not yet evolved, but microbial mats and colonies are torn apart, scattered like dust before the storm. The planet shudders, and for a time, silence reigns again. The Sudbury event was not alone. Other large impacts scarred the Proterozoic Earth. The Vredefort Dome in South Africa, though older, remained a looming memory. Each strike was a reminder that Earth's story is shaped not only from within, but from without. The skies themselves carried dangers that could rewrite the surface in an instant. Yet, paradoxically, such violence may have nurtured resilience. Impacts may have sterilized some regions, but they also created new niches, craters that filled with lakes, hydrothermal systems, fueled by heat, fractured rocks that became shelters. Just as volcanic fire gave nutrients, cosmic fire gave opportunity. In catastrophe, life found ways to adapt and persist. Speculatively, could these impacts have been hidden teachers? By pushing life into extremes, forcing it to survive darkness, acid, and chaos, perhaps they prepared it for future challenges. The Proterozoic biosphere learned to endure sudden shocks, to scatter into refuges, to rebound after devastation. This resilience would be crucial when more complex organisms arose, inheriting a planet that had been tested by fire and stone. As you reflect, imagine Earth not as a quiet sphere, but as a world in dialogue with the cosmos. From deep within came fire, from the skies came stone. Both struck with violence, both threatened to erase, yet both also shaped the conditions for endurance. The Sudbury Basin and other craters are not just scars, they are reminders that life on Earth has always lived under trial, and that survival often means finding strength in the shadow of disaster. Across the Proterozoic, the Earth was tested by fire and stone. Lava flowed in endless sheets across continents. Asteroids struck with unimaginable force, leaving craters that still scar the planet today. To us, such events feel like the end of the world. And yet, in those moments of devastation, life did not vanish. It adapted, it endured, and in that endurance, it became stronger. For microbes, survival meant flexibility. When ash darkened the skies and photosynthesis faltered, they retreated into sediments, feeding on chemical gradients rather than sunlight. When oceans turned acidic after eruptions or impacts, they clung to niches where conditions remained stable. Hydrothermal vents, deep underground aquifers, and cracks in rocks became sanctuaries, hidden worlds where heat and chemistry provided what the surface could not. Life shrank into refuges, waiting patiently for the world to calm. Mainstream science finds proof of this resilience in isotopic records. Carbon cycles show dips and recoveries that match environmental shocks. Microfossils vanish from some layers but reappear in others, evidence that lineages persisted even through planetary upheavals. Life was never erased completely. It found new ways to persist, even when catastrophe reshaped the surface. Speculatively, one might see disaster not only as destroyer, but also as teacher. Each crisis tested the boundaries of survival, forcing life to become adaptable. Fire burned away the fragile, impact shattered the comfortable. What remained were lineages hardened by trial, ready to explore new possibilities when stability returned. Without catastrophe, perhaps life would have stayed simple, content with microbial mats and passive existence. Instead, adversity demanded innovation. Imagine a world after fire. The land is black with cooled basalt, rivers of stone stretching to the horizon. The air still tastes of ash. In shallow pools, microbial films begin to return, feeding on minerals leached from fresh rock. From destruction comes fertility, nutrients that fuel new blooms, new opportunities. Life does not merely recover, it rebounds with vigor, filling the niches carved by disaster. Now imagine a world after impact. The crater still smolders, its edges jagged, its center filled with molten rock. In time, rain fills the basin, creating lakes rich in chemistry. Microbes colonize the margins, exploring environments that never existed before. From shock and violence emerges novelty. The scars of Earth become laboratories, teaching life to exploit extreme. Speculatively, we might even ask, was catastrophe necessary? Without cycles of fire and impact, would life have remained fragile, unprepared for greater challenges? Was it hardship that forged the resilience needed for complexity to evolve. The Proterozoic reminds us that endurance is not born from comfort, but from trial. Life learned to bend, to scatter, to adapt, until resilience itself became its greatest strength. This paradox carries into the present. The oxygen we breathe, the shells we build, the diversity we celebrate, all of it rests on a foundation laid by ancestors who survived crises. They learned to persist in silence, in darkness, in violence, and through that persistence, they carved the path for us. As you reflect, imagine catastrophe not only as tragedy, but as transformation. Every flood of lava, every falling stone, every moment when Earth seemed most hostile, was also a lesson written into life's memory. Survival was never about avoiding disaster. It was about enduring it, learning from it, and rising stronger. The Proterozoic was an age of resilience. In its crucible of fire and impact, life discovered what it meant to endure, and in that endurance, it prepared itself for the future, ready to face the Cambrian dawn, ready to step into complexity, ready to become the life that still walks the earth today. The Proterozoic is often called a hidden eon, a time overshadowed by the dazzling Cambrian that followed. Yet, in its long expanse of nearly 2 billion years, it carved the foundations of everything we know. It was the age when continents gathered and broke apart, when oceans shifted from alien chemistries to oxygenated waters, when fire and stone tested life, and when the first fragile steps toward complexity were taken. To understand this eon is to glimpse the roots of our own existence. Imagine, for a moment, those ancient seas. At first, they shimmered with iron, stained red and green, their waves alien to our eyes. Then came the slow breath of oxygen, seeping into the world, both poison and promise. Frozen equators, stretched in silence, the planet locked in ice, before fire and greenhouse gases broke it free again. Microbial mats ruled like empires without monuments, and from their invisible cities came the first alliances of cells, the spark of multicellularity. Then came the Ediacaran, when soft-bodied quilts and fronds drifted across the seafloor like dreams given form. They were fleeting, their beauty fading before the Cambrian dawn, but they remind us that evolution is not a straight march forward. It is an exploration, a sketchbook filled with experiments, many of which never survived, but still shaped the canvas of possibility. The Proterozoic was not gentle. It was marked by cataclysms, volcanoes flooding continents with fire, asteroids carving out vast basins, climate swinging from frozen silence to storming greenhouse. And yet, through all of it, life endured. Microbes hid in vents, in sediments, in fractures deep below. They waited, adapted, and survived until resilience itself became the defining trait of life on Earth. It is in that endurance that we find the true legacy of the Proterozoic. Speculatively, one might see this eon as Earth's rehearsal. The continents breathed in cycles, the skies shifted, and life was tested, again and again, until it was strong enough to embrace complexity. By the time the Cambrian dawn broke, the groundwork had been laid. The stage was ready. Reactors, cells, colonies, creatures with shells were prepared for the explosion of diversity to come. And now, as you return from this journey through deep time, imagine the echoes of that hidden world. Picture the stillness of a frozen equator beneath a pale sun. Picture the red-stained seas, their iron falling into bands of stone. Picture soft-bodied creatures swaying in alien currents, and microbes clinging in silence through fire and impact. These are not just distant memories. They are chapters in the story that led to you, to all of us. As you rest tonight, remember, even in Earth's darkest ages, life found a way.